Hi, this is Stephen Brower from Raton Valley Community College. This video is to discuss or to show a remove algorithm for a binary search tree. So one, I want to talk about prerequisite knowledge. One of the things you should take a look at in terms of a video I created is the video I have on the exists method. So there's another video. It says part one exists, or something like that, where I go through the algorithm that I have here for moving cursor down the tree to try to find what we're looking for. So it went through the looking for apple, the looking for raspberry, and the searching for cantaloupe. And the reason why I do want to point that out is the first aspect of the remove algorithm is going to be a loop where we have to move cursor down the tree. And so I'm going to go through that first part pretty quickly because I'm assuming we just would have seen the exists method. So if you haven't seen exists, go and take a look at the exists video and then pick up here in terms of the remove. And so the pseudocode that's here, it's except for this thing of parent, which we'll get to in a moment, basically all of this pseudocode that is here, except for parent, is the same as the Java code that is here for the exists. Meaning when you actually have to go and write the remove algorithm, you can use the exists method as a template for what this first piece will be in terms of the loop. So the remove, now I do have two slides, and the slides are in Canvas. There's two slides, part one. Remove part one and remove part two. So there's the loop, and then these are the conditions that are after the loop. So the algorithm is listed there. Where was I going with this? Couple things. One, there's 200 to 300 different algorithms out there that exist for binary search trees. So if you pick up a different book, odds are you will see a different algorithm. The one that is here that the author has put in as a simplistic, it's not going to seem that way, but as a simplistic remove, can be implemented in about 25 lines of code. Some of the other remove methods, one of the ones I had worked on for a graduate class that also was dealing with balancing, was about 300 lines of code just for the remove method. If you pick up a different book, look at a different resource, you're going to see an algorithm that is very different from the one that's here. This is matching the algorithm that's in the Michael Main book. He describes the algorithm in text. So what these two slides are here is sort of a distilled version of the algorithm that Michael Main has in his book. But the remove, the first thing you have to do is find. Now I want to go through 4 possible scenarios for removal, which will match our conditions that we're going to see here. And so what I want to do here first, and I'll probably go very quickly, is just move the cursors, move the pointers, and get to the point where we have what we're looking for. Okay, so initially when we begin, so when the algorithm begins, cursor is going to be root, parent of cursor is going to be null. The parent is something we're going to see later that some of the conditions will handle. And so in terms of the top of the loop, it's saying, is this what we're looking for? So is target, which is kumquat, equal to cursor get data? It's not. So then parent is going to then become cursor. And I can get rid of the null here. So parent becomes the cursor. And then cursor needs to move. Well, in this case, cursor is going to move. I did that wrong. Cursor needs to move to the right-hand side. What we're going to be doing as we're moving down the tree is we're going to be sort of moving in tandem cursor and then parent. And I believe I have it as parent of cursor, but it's the parent node. So we'll be comparing again. Is kumquat the same as lemon? No, it's not. So then do we move left or we do move right? Well, here we're going to have to move left. Parent comes down here first, and then cursor, in this case, will move to the left. So again, we'll ask the question, does kumquat equal cursor get data? It doesn't. So the parent will come down here, and then cursor will move to the right. Kumquat, grape, they're not the same. So parent will come down here. Cursor will move to the right. Is kumquat and cursor get data, which is the kiwi, are they the same? They're not. So parent will move down to kiwi, and we just parent will come down to kiwi, and what will happen is cursor will become on cursor get right. Sorry, cursor is going to become null, and so let me just edit. When cursor goes to the right of kiwi, cursor will become null. Okay, so for the first part of the remove, which is the loop, if we were searching for kumquat, when we come out of the loop, cursor would be null, and we didn't find what we're looking for. So if we were looking for kumquat, when this loop would finish, when we come out of the loop, the situation we would have here is that cursor is null, and we haven't found what we're looking for. Now, we'll revisit the conditions. I just went on these 4 searches, do the same thing, move the cursor and the parent. I might just be a little more quick as I do the other ones. But we want to remove apple. Well, we found it. That was quick. Okay. So we'll look back at one of the conditions, but in this condition here, when we look at, it's a particular condition, but at least the pointers are in the right place. So this one here, we want to remove raspberry. And so what will happen is we will have to move our parent. This will become parent. Since we're looking for raspberry, cursor will move to the right. Plum isn't raspberry, so the parent moves to where this is, and then the cursor moves to the right. Oh. Cursor moves to the right. Cursor get data isn't raspberry, so the parent will come to here. And then the cursor will move to the left to raspberry. And so now we found what we're looking for. And this is a particular condition, which we'll get back to in a moment. But that first part, the loop, has moved cursor to the node that we want to remove. And so just jumping back again. So this scenario 1 here, cursor became null. We couldn't find kumquat. This scenario here, cursor, we found apple. It's up here at the root. This scenario here, we're trying to remove raspberry, and so cursor is here pointing to raspberry. This last condition that we haven't gotten to yet is we want to remove cantaloupe, and what will happen on the first thing, so cantaloupe is not cursor get data, so the parent becomes cursor. Cursor moves to the left, and boom, now we found what we're looking for. So we will revisit these 4 conditions in a moment. And what I just want to do is iterate again. The first part of the remove method is going to be a loop. That loop will look very much like the exists. What the exists did not have is parent. So imagine if we also had here parent equals null. And then here we had parent equals cursor, then cursor equal cursor get left, parent equals cursor, cursor equal cursor get right. But that first part of the remove is the loop. And what it does is it moves cursor down the screen, down the tree, left or right, and it moves the parent along with it. So when this loop is done, we either found what we're looking for, or we didn't find what we're looking for. But in terms of the conditions then, well, that's what we'll take a look at here. Now, again, just as a reminder, this accompanies the Michael Main book. There are 200 to 300 other algorithms out there. You pick up a different book, you Google, you'll find different algorithms. This is meant to be a simplistic approach that will end up being about 25 lines of code when it's turned into Java. As an introductory remove algorithm, it's simple. It gets the job done. There are gaps in this algorithm. And it's one of those things that some of the later conditions will handle things an earlier condition with a subclause could take care of. But anyway, so we come out of the loop. There's 4 possible conditions. Now, this is going to turn into an else if chain. So you're going to have if cursor is null, else if cursor is at root with no child, no left child, else if cursor is not at root and no left child, and then the trailing else will be this condition right here. So the first condition, cursor is null, that was this one right here. When we fell off the tree, cursor was null. Now found already is set to true, but the reason why we would want to, and if we were to do the Java equivalent of it, this is something I would kind of mention on the board, is by having this if statement here, if cursor is null, then whenever cursor is being referenced here, we know it's not null, and it's not going to, or the compiler is not going to raise a potential issue. NetBeans would, if we refer to cursor right here in this next one and didn't check to see if cursor was null, then it would flag it yellow and say, hey, there's a possibility this can be null. But by explicitly seeing if it's null, then we're not going to get that as a warning. But the first condition, again, we didn't find what we're looking for. And so if cursor is null, we'll just say that we didn't find it. Found is false. The second condition, now this is a special one, and that is, well, what if we're at the root and there's no left child? So here we're trying to remove apple, and we're at the root. So the root and cursor are the same thing. Now, one thing, if I jump back here for a second, the test for cursor is at root, we actually can do equals equals, because what it's doing is it's comparing the pointers. Do these things point to the same thing? So cursor equals equals root is going to be looking at the memory addresses, and so it's going to find out, is this memory address and this memory address, are they pointing to the same thing? If it is, then all we have to do is move root equal root get right. Meaning if root is here, and from here, if we do a get right, we get to lemon, then the execution of this statement, root equal root get right, that will move root to the right here. And root is now pointing to lemon. Lemon is now the root of the tree. We maintain binary search tree order. And so that is, that is the second condition here. So remember the first part was if the cursor is root, and the other thing is making sure cursor dot get left is null. That's the Java sizing of this pseudocode here. So this else statement here is if cursor is root and the left of cursor is null, then we can promote the right child to the root. We can promote the right child to the root, which is this little bit of text that I have here. So then the promoting, I'll do using, I'm sorry, this is me being a little OCD right now. Okay, using root equal root get child. And I just realized that I have run out of time for this segment. So there'll have to be a part 2 of part 2 for the remove. Right now I only got through two conditions. That's it for now.